And welcome everyone to the Atelier3D MCIN tutorial. My name is Louis Borgeat. I'm with the Computer Vision and Graphics team at the Digital Technologies Research Center at the National Research Council of Canada. And today, hopefully this will work. I have three other presenters with me for this tutorial. So I'm one of the original lead researcher for the Atelier3D development project. With me, we also have Philippe Massicotte, also with NRC, who's been since the beginning one of the main software developers and software manager for Atelier3D. We also have with us Mona Omid, who's working both with us at NRC and with the McGill Center for Integrative Neuroscience, so with our McGill colleagues, and where she's working on improving 3D structures extracted from annotation work in the BigBrain and other work, and who's also involved in developing new features within A3D and will be describing her use case. And we also have Andrea Brandtstetter from the Institute of Neuroscience and Medicine, who will be providing more of a user perspective on A3D, as most of the other presenters are more on the computer science side of things. So for those who have not been involved with A3D at all in the past, so just a very quick history. Atelier3D originally is a software for local and remote, very large data set visualization, but in many domains. And early in the development of the BigBrain, we made a version specific to really enable a quick 3D visualization of intermediate results in aligning and correcting data in the BigBrain with colleagues in Montreal to support them in that. With time, the software became a tool for people who started to do delineation, mapping, and research in the 2D BigBrain slice to be able to validate their results in a 3D environment before there were any web tools or other alternatives. And with the years, it became a tool where you can do develop your own atlases, do delineation, extract 3D surfaces, document your work, and organize it in the full software environment that is Atelier3D. So for the tutorial today, I have prepared a huge PowerPoint that we'll mostly not use. It's more meant as documentation. You can download it from the shared Google Drive for the course, with plenty of other material I'll mention. So the presentation contains a lot of core information on the software, features, capabilities, how to execute some of the use case. We'll go quickly through its current status, features, and some of the underlying technology, but that's really not the goal per se. The tutorial will be mostly going through, in fact, videos, in this case, of going through some of the use case. So visualization, organizing, creating data in Atelier3D, organizing a large workspace, importing and exporting data from other tools, and go into a more in-depth example of how you can create your own map of structures in the BigBrain dataset. And then we'll go through some use cases and hopefully have time to answer questions as we go at the end. And we can run the software live, obviously, also to answer questions and go into other directions. An hour for this software is rather short, so we'll go quickly. Hopefully, you can try some of this on your side. You can down. So I'll show later exactly what we have available, but you should be able to reproduce most of what we're showing today. In terms, and those are slides I want to go through very quickly, of what the status of the software is. So one way to look at A3D is as a complement to some of the web tools. It is a C++ based tools you need to install that comes with a lot of utilities that allows you to do advanced visualization at 20 micron. We've tested it with 1 micron. You can have your histology volume meter local or remote. For 1 micron, it's probably going to have to be remote as the data set grows. And it's really centered around the workspace where you can have hundreds of intermediate results, meshes, compare them, overlay them, and structure them in a way that you can really use it as a workhorse, basically. And there's a lot of computer graphics material behind it. We won't really go there. There's also all the tools to do surface extractions from contour and annotation, create contours from those surfaces and loop, and there are use cases around that. We'll describe some of it in terms of the underlying algorithms. There are a few slides that, again, the focus really will be today on using the software. In H3D, you can import a lot of things. So you can convert Ming stacks or Ming volumes into loadable format, raw data, OpenVDB, which is a very powerful sparse voxel format from the computer graphics world, all the mesh format from OpenScene Graph, MNI, OBG. There is also import-output from SVG files from some of the web tools also. And today for the tutorial, we've only provided instruction on the Windows version to keep it simple, but there's also a Linux version, which is actually preferred if we use converters and start from scratch in the long term. There is documentation in the software. There's a help button with a lot of information on visualization, not so much on actual surface extraction, things like that, but today we'll be covering some of that. In the shared drive, you have an H3D download links, the installer. So it's a Windows installer, you just double click it. Then you need to send an email to Philippe to get a free license, just so we track where it goes. But it is free. We're even open to share the code. So it's really just a management tool. Again, the PowerPoint is there. There are some intermediate files that you can load that are also there to reproduce some of the examples, so you don't have to start from scratch. And I guess that's it for now. Oh, very quickly. So H3D, as I said, was not designed originally for brain mapping. And so there are many menus and things that we've tried to add, but that you might hit that relate to other applications. Those are actually all screenshots from the software, except the photo on top of aerial mapping project, heritage project, large scale environment mapping. So there's a lot in there. We've tried to reorganize the user interface so it's really intuitive for people in neuroscience, and most of what's there is of immediate value to you. Just giving credit to all the other people's data set we'll be using to show the software features. So there's an atlas in development by Dr. Sedziko and Altinkaya in McGill. So we'll be seeing some intermediate results of that, some work by Sherry Jones and PJ and Claude in McGill. Andrea Brandtstetter will be one of the presenters, and we'll be also showing very quickly how to import and visualize some of the cortical layer work by Konrad Wagstael. Done with the PowerPoint for now. So we'll be now mostly looking at the software for a few use cases. So this first very simple video is simply how to run the software and do the most basic visualization. So when you start it, you go in the workspace menu and open a .h3d file. A .h3d file is a workspace. So it contains a pointer to your BigBrain or other dense histology data, either locally and remotely. In the instruction, it's remote, it's local for today. And this video basically tells you what the left wheel mouse for scrolling and middle, so what the three buttons do, which is, I believe, identical, hopefully, to what the tools we've seen up to now on the web are doing. F for full screen. So really, this those are the basics. It should be intuitive, but you have this as a reference. When you load it, you also have here the workspace. So this is everything contained as a supplement to the BigBrain or your histology itself. So if you have an atlas, if you have intermediate results, they're all organizable, displayable here, as we'll see as we move forward. So Philippe, don't hesitate to intervene, or anybody else on the panel if I'm missing obvious things. I'm trying to go quick so we have time for question. So now a simple illustration of what you can do with the context quadrant. You'll have to do some exploration. There are a lot of simple, intuitive options on how to configure what's displayed. There's actually a full recasting module available. Right now, in the quadrant, we're displaying a version of the BigBrain, so recasting is of limited interest there, but you could have an aligned MRI or something else displayed there as a reference where this would become more significant. What we're more displaying here is the high quality transparency for the meshes of our draft atlas here being manipulated. So here I'm making all the surfaces transparent, and then as you can see, well, if you follow the mouse cursor at the bottom left, how to selectively make, so I'll go back very quickly. You can see that we're making some of the meshes selectively opaque, and there are kinds of features like that. Another interesting pointer is that if you control click on any surfaces, it will take you to that structure in your own organization, and control left click actually. And if you shift click, then you can move the 3 slices to that point in your visualization here. And so move the intersection, the cross to that location. So again, many other things to look into, tools for measurement. We'll try to go through a lot of them. Should I pose for a question or two? None for now, or one answered? Okay, so Philippe, intervene if we need to stop. Another feature that's been very popular for those type of application is the ability to develop oblique or new reference frame. So H3D is as fast when displaying in the slices in the native axis or something orthogonal to it as to do oblique cuts in the brain. So you can define new reference frame if you want to visualize your data in the same axis as other atlas and do comparison. Or this is one use case. There are many others. So you can define a reference frame. Here we're naming one that we want to keep. In practice, for the tutorial, we'll be focusing a lot on the subthalamic nucleus as a target structure to model because it's small and actually easy to delineate. So as a tutorial target, it's quite appropriate. So to create our reference frame here, you can see that they are manual, very graphical tool to do it. So you can draw lines to set new axes in your reference frame. And we'll see other of those manual tools in the next few seconds. So just rotating axis around and things like that. So this will have value in certain cases. In other cases, you will have numerical values and actually information you want to type in to define those new reference frames. This is what we're going to see in a few seconds. So you can create as much as you want, save them, organize. They go in your workspace, which is in the end a big XML file with pointers to all the things you've created that you can organize on your file system. So here I'm changing the origin based on the location of the cross, and you can set normals for some of the axes, do cross product to set the others, etc. There are many things you can explore on how to do it. Here we're looking at a rotation option using different representation, etc. And in all the videos, you have some text I'm ignoring now, but all the videos are available separately in the download folder if you want to use them as documentation for some of the feature. So now, and this gets confusing, you'll have to play with it. With the buttons here on the top left, you can switch from different combinations of, okay, I missed it. I'll just state it quickly. Of your oblique reference frame, the native one, combine both, and see the axis of one in the other. So we were saying that at the end of the video. So there's some of that here when you can reference one in the other and do your slicing in either using all those buttons here at the top. Okay. So I see a question on nifty files. So in terms of converters, I guess we can discuss later. Right now, we test mostly the pipeline with Mink in terms of converting from images. So if you convert them to Minks first, then we're very optimistic that you should be able to use our importers. In theory, there is a path per se. Philippe might want to comment some more on the current status of things. One of the use cases we present at the end is really about improving our interoperability tools with different formats and keeping them up to date. So this next example is about importing data in your workspace. So what I'm doing now is creating what's called an annotation task. Basically, what characterizes a subtask is your ability to set different color and labels to all the annotation. The annotation file per se, for a voxel annotation, it's really a numeric tag for each voxel of your histology, 3D histology, and then you convert that to names and color through those files. So it can be displayed differently in different contexts. Here we simply imported a file in the H3D format of the Conrad's waxil cortical layers, and now we're doing the same with the meshes that are available on the cBrain FTP site with the BigBrain. And they are in the slide at the end, example of converting Mink stacks into that type of overlay H3D sparse file. And there are slides explaining what an H3D sparse file is also, which I probably won't cover verbally in here. So what you're seeing in the video while I'm talking is really the ability to turn on and off all structure using checkboxes. And this is hierarchical. If you have a large hierarchy that you've created by creating groups, you can turn things on and off and manage actually a lot of data efficiently that way. And you can, again, play with transparency recasting here and change the colors by changing the color space, as we will see a little later. Our next example, we're going to now create a material inside H3D directly. So we're back to the subthalamic nucleus, and this time we want to create point of interest that we can move to automatically to document our work, and lines that could correspond to structure or things we want to highlight. We'll also show how to name them and display them in the quadrants. So here I'm creating simply as using the menu from the cross, the subthalamic nucleus point of interest. We're going to create a few other points around it just so we can create a line. Basically, in H3D, the way you create a line that corresponds to some structure of interest is by creating 2 points, selecting them, as we'll see in the menu here, and turning it into a line, which is what we'll see. While this occurs, okay, yes, we can change colors, names, and when we're done, now we create our line, which has a name by default. I can't see. And you see here those small tags. If you click them, you can actually display the labels. So you can display, oops, I posed it unintentionally. So this applies to all meshes, structures. There's always that tag that you can click to display the label to produce figures and create learning material. And once you've created those structures, you can always move to them. You can see now that they're transparent when they're not in the plane. And as we navigate to them, they become more opaque. So we can also see structures that are behind the current plane and create and change their color to name map. So I think I will end that video here because there's a little overlap with the next videos where we actually will be starting to do some delineation of our subthalamic nucleus and creating meshes from it. Okay. So we're back to the subthalamic nucleus and we're moving from visualization and simpler aspects into actually starting a mapping process. Okay, I posed it again, apologies. So I am creating again a new annotation task. And this time we're creating a contour, which is basically an overlay that we can draw. So it's the exact same format than the first cortical layer we opened. It's just a different use of that same format. This time, because we're actually starting our mapping process, we'll start naming structures, giving them numeric IDs in that file. So we'll be able to then process them to extract meshes. So basically, you can see the window for drawing here that appears when you click the brush. The idea is you use ID 100, that yellow number in the annotation is really to define a contour that can be shared by multiple structures. So it can be a frontier. And then to inform the software, the reconstruction algorithm, you'll put a dot of color with the other pen tool here. That's not the contour, but that's the dot, to identify that this enclosed area is our subthalamic nucleus, and that information should be used for the reconstruction. And in this process here in the video, you can see that with page, well, you can see that bit, but using page up and page down in that frame, you can move by block of 20 layers. So in the process normally, and we'll discuss this when we talk about typical use cases, but because the BigBrain is very large, most users will do their delineation for structures every 10, 20, 40 slices. And then the reconstruction will interpolate. You'll obtain a mesh that you'll want to improve by then fixing, making fixes in the in-between layers, as we'll see. What was happening was I was talking about something else, which is of importance, was a demonstration of the undo feature and the eraser, basically. So we can move back a little.
So I may have added that you do not need to keep a regular interval. It can vary, but the maximum amount between the contours has to be kept in mind, as you will see further. If you exceed a certain number from the extraction parameters, you'll see soon.
Yes. So here, there's a little cheat in the video. You've only saw us annotate 3 layers, but we're going to presume that more had been done so we can extract a complete surface now. So we're going to save our work annotation. So now we're saving just the file. We could save the workspace also. So we're also saving the name maps and everything. So we're okay. Yes. So I think when you click that one, apologies, that means saving everything. And so there's a button to save only the file you're working on and one to stabilize. So there is a save as in the workspace, and the software is capable of managing many intermediate results. Don't hesitate to keep multiple versions. So now we have our annotation file, and we're going to extract a surface from it. So you could see in the menu, the context menu on the surface. So the surface will extract will have the timestamp in the name. You provide the directory and the prefix. You inform the algorithm of how far it should interpolate between slices. So if that should be the number of slices between your annotation. Basically, if you haven't annotated up to small areas at the end and you're working on a single axis, then the cap 8 really is the extrapolation part. If you're annotating multiple surfaces, it will do all of them unless you specify one. The filtering is really a very basic smoothing that you can pick an amount of. Right now, we're using annotation on one single axis. The software allows you to combine annotations on multiple axes and will then interpolate between distance fields calculated separately on each of one. So in this example, we're only using our contours in the coronal axis, as you've seen. And we will be, okay. So it is starting. You can produce a mesh, you can produce a voxel marking of the entire interior, or you can produce a complete distance field, a signed distance field actually, in the OpenVDB format for each of your structure at this stage. So for a small structure like that, it's almost instantaneous. It will take many minutes for a big structure and might require a workstation for a very, very large one. So we're done. We now see our surface here and the intersection of our mesh with the annotation. So our mesh here is brown because we've picked that color for the subthalamic nucleus. And we can evaluate the quality of our very approximate reconstruction here.
I have just a short comment to the annotation. It is absolutely necessary or important that there are no holes within your annotation. So as soon as there is any hole or something, the whole process cannot be done. But you will be informed anyway during the process, and it will tell you then, you can click then on the coordinates whether how you where is the hole and whether you can need to do any corrections or something.
I believe this is what we are actually about to show as part of the video. No, well, you were right on what needed to be mentioned now.
I would like to add that this delineation was done as a demo purposes and not done by an expert. So this is really just to demonstrate the tools and not be used as a reference.
So you can see here in the reconstruction that, yes, there was a gap, as Andrea was mentioning. If you have a gap, the software will not try to complete it. It will mention that your contour for which you had integrated a marker for a structure is not closed, and will, by clicking on the button, you can be taken to the slice where the problem is and correct it. So there are a few safeguards like that in the software. It's not perfect, but most of the time it will make it possible to fix mistakes relatively easily. And this last example is what happens if you forgot to put your marking dot and your contour gets ignored by the reconstruction. In that case, we have a distance of 40 slices then between two contours. And then we'll simply be displaying the gap. And, so if this happens, it means you forgot to mark one of your annotations. Okay. So the next video is a continuation of that, and it's really the beginning of the illustration of how a lot of people have been using Atelier3D to build maps of some structures in the recent past. This is something Andrea will be able to comment on more largely, how you go from that course results and then move into more detailed structures and correcting smaller and smaller errors in the process. So in this video, we're continuing the same example, but here our goal will be to presume, okay, this here is not desired. There's a problem in our mesh that we want to correct. So what we'll do, instead of drawing new contours from scratch or fixing the one we have, we'll use the menu that extracts actually drawings or contours from a mesh. So in that menu, we pick our mesh that has the problem, and we inform it that we want for that structure to create new slices. And I'll just pause it so we can see. This time, however, we'll want to have annotation not only on the coronal, but also on the sagittal axis, so we can refine our work doing drawings on both sides. Continuing. So I'm not sure how well it shows on everybody's screen. One important thing to notice, now we have annotations on multiple axes. You can see that whatever is a drawing in a specific axis appears in transparency as an intersection in the other ones. So you do have 3D visibility. So you can see here every 20 slices, the intersection of those yellow drawings in that axis, and you can see both axes here. So there is that element of visualization that is very important. Here in the video, well, again, as Philippe was saying, this is not professional work. It's really for the tutorial. We are quickly making modification to our auto-generated drawings to try and correct that problem here. And once we're satisfied with that, we'll resave our annotation and go back to extract a surface. And you can see how the process will be to iterate, augment the density of the drawings, fix them, keep them as the reference, create new meshes, and iterate progressively. There is no right now operational feature to deform the mesh directly and go from there in the software. It's being discussed. There are prototype version of it, but it's not there per se. And the logic for now is you want to keep the annotations as the reference and the meshes as the output. So now we're opening the second mesh. We see them in overlay. We could change their color, make them transparent in the other quadrant to do some sort of analysis. We hopefully through Mona's work, we will have quantitative analysis of difference between meshes straight in the software. It's not there yet, but it's coming. And so we're actually doing extremely good on time. meaning it should have probably taken more time to discuss some features, but we can do it live at the end. That might actually be excellent. So back to some of the slides. So this is really the same expression of what we've been describing, and that probably users should be more talking about in terms of how A3D can be used to build atlases and delineating structures and improving the quality of other structural mapping. So it's really that idea of iterating between meshes and work. Just to mention, it's in the slides later. They are scripts and converters to convert contours that have SVG or JSON work done in other tools. You do need to figure out the reference frame conversion that the converter will not do for you, but otherwise it's possible to import them in A3D. And also to slice, I believe, Philippe, some of the meshes into JSON files also. So again, another description of the workflow, but maybe now I would like to let Andrea give her user perspective on this.